Hi, welcome back to RISC-V instruction encoding. We have just covered the R-type instructions that perform register-to-register arithmetic and logic operations. So let's see how we can support similar kind of an instruction, which are those that work with the immediates. Ideally, we would like to use the same instruction format for all possible instructions, but that may not be quite practical. However, we would like to reuse the placement of most of the fields across different formats. So what we'll see here, we will need a different format for I-type instructions, which are our instructions that work with the immediates, but we'll try to see how we can make it to be similar to the R-type. So let's review how do the register-based add, how does the register-based add instruction look like, and how does its immediate counterpart look like. So register-based add takes the value from register RS1, adds it to the value of register RS2, and stores the result in the destination register RD. Its immediate counterpart, add immediate, takes the value from the register RS1, adds the immediate, and stores the result in the destination register. So what is that immediate coming from? Well, it has to be encoded as a part of the instruction. We clearly cannot use all 32 bits in the instruction to encode an immediate, so we need to use just part of an instruction. What can we repurpose from the R-type? Well, we can see that RS2 is not being used, so we can use that. But RS2 only has 5 bits. 5 bits is just not enough of a range for an immediate. It would give us only 32 different values, covering the range of signed integers from -16 to +15. So we need to add a new instruction format where we will repurpose other fields in the instruction format. So let's review what we see in the R type. We have the opcode on the bottom, then we have 5 bits for the destination register, 3 bits for func3, 5 bits for RS1 and RS2 fields each, and then we have the top 7 bits dedicated to the func7 field. What are we going to do in the I-type instructions? Well, we already agreed that we're going to repurpose the RS2 field, but we are going to add the func7 field for that, to that. So what is going to happen? We drop that and make one 12-bit field that is going to be storing the immediate value. Notice that in R-type instructions, we use one opcode. We are going to have a new opcode for I-type instructions. Also, with R-type instructions, we were kind of sloppy in, we didn't use everything that all the bits that we had in the instruction. We had left over some of the func7 fields. We have to be careful how we are encoding things for I-types, because if we are sloppy, we will lose the range for the immediates. One thing that we will ask ourselves, how many different instructions do we need to support in this case? There are 7 instructions that we have seen so far. We are going to see that we need to add 2 more to our base instruction set, so we'll have 9. Func3 field can encode 8 different instructions, so we'll use a trick to add the 9th one. But nevertheless, we are now able to support 12-bit immediates, and they cover a good range. That is something that we are often going to see in the assembly code. This range of immediates is going to cover a wide range of, say, loops. The range of this immediate, since it's 12 bits, covers 4096 values, going from -2048 to +2047. Keep in mind that since we are always using that immediate together with a value from a register RS1, which has 32 bits, we have to sign extend that value to 32 bits. What is sign extension? It is an automatic operation that processor performs where it extends that top most significant bit of the immediate across all the most significant bits. Basically, remember that thing where we smear that sign bit over all the bits to preserve the sign of that integer. So if that sign of the most significant bit of the immediate is 0, we copy 0. If it is a 1, we copy all 1s. Keep in mind that sometimes we'll need wider range than 12 bits of immediates, and we'll see that later, that we'll use another instruction to cover that. Let's take a look at an example for the IFormat. So let's take a look at an assembly instruction, add immediate x15 x1 minus 50, which takes the value from the register x1, adds minus 50 and stores it in x15. This is essentially a subtraction because remember, we don't have sub immediate. Immediate types have a different opcode. Opcode here is 001 0011. That is different than what we have had in R-type or register-based instructions that had 011 0011. Now what we need to do is to fill the rest of the fields. So we will put the RD value of 15 in the RD register and RS1 value of 1 in the RS1 register. We'll take a look at the green sheet and find the add has a func3 field of 000, which happens to be the same as what we have seen in R-type instructions. Finally, we need to encode the immediate value in the top 12 bits. So here immediate is minus 50, so we need to write 2's complement value in the top 12 bits of minus 50, which you can verify is true. This one has a value 32, 16 plus 1, 49 plus 1. To get it inverted is minus 50. Let's recap what we have seen of IFormat arithmetic and logic instructions. There are 9 of them. 7 of them we have seen before. So this is add immediate, XOR immediate, OR immediate, AND immediate, shift left logical, shift right logical, and shift right arithmetic. All of them immediate. There are 2 new instructions that we have here, SLTI and SLTI-U. SLTI compares the value that is in the source register with an immediate value, and if the source register value is less than the immediate value, sets the destination register to 1. Similarly, SLTI-U does that with unsigned numbers. Take a look at a few interesting things in this table. First, all func3 fields are the same as what we have seen in registers type instructions. That is very convenient. That basically means that we are going to recycle that part of a microprocessor that will have to figure out what kind of an instruction we have there. Then take a look at this way. What are we doing with the shift amounts? The amount of shift is limited to 5 bits, because if we shift either left or right by more than 5 bits, we have already inserted all the zeros into the register, and using larger shift amounts is meaningless. We are not going to do anything other than just keep shifting in zeros. So we don't need to support that. That's why our shift amount is limited to 5 bits. And then we have these top 7 bits of the immediate value free to do something else. In this case, we're using bit 30 of the instruction to encode whether we are doing logical or arithmetic shift right, which basically means whether we are sign extending or not. And notice that it is done in the same bit position as we have had for the register-based instructions. And that's it. That summarizes the I-type format, and we are going to move on to the next section in a bit.